Okay, so good morning again, everyone. So we will start the class now, and we are still in chapter 2. And last week we have learned some of the combinational logic or combinational circuit already. So we have done this. So until adder and subtractor. So we have done subtractor. We have learned the decoder. We have learned the multiplexer, the adder, how addition is done in hardware, uh, more than one bit adder here. All right, this is full adder circuit, and this is a ripple carry adder. All right, more than one bit adder. And of course we have other kind of adder as well, the fast adder for example, but we not cover in this course, so you can check that kind of adder also if you want to design a fast adder, for example carry look ahead adder. Or we have a more cost efficient adder, a serial adder, where we can look in chapter 4. All right, so there are many kind of adder out there, and the of course the very popular one is the ripple carry adder. And we have looked at the sign number, how we represent sign number in digital or in hardware, how we use sign number in hardware, where we use second complement instead of first complement. And the reason why is that the design where if you use first complement in addition, yes, you can do that, you can get the result also, but you need to have two adder or add two times like this. For example, if you have carry here, all right, in order to get the correct result, for example, you have 5 minus 2 and the result should be 3. All right, so when you use adder, remember in hardware, when we add or when we sub a number, when we subtract a number, we actually use adder, and we sub or we add to the complement number. So in this example is the first complement number. So you can see when you use adder, you can add, and the result is not correct unless you add the carry here. You add again, then you have 3. 5 minus 2 is 3. All right. So you can see that you need 2 times addition. But if you use second complement, there is no need to do that. All right. So you can see that when you have 5 minus 2, this is 5, this is minus 2. All right. And you use adder, see, and you get 3 here. Okay, that's why we use second complement in our computer, in the hardware. Okay, and last week I gave you this assignment. This is the what we call the adder subtractor unit, and I hope that you can do this. You need to use the software, the Quarters 2 software, to write the code for this. And of course, you need to start with your 1-bit adder. All right, and you need to use the hierarchical design methodology to connect all of your adders to be a 1-bit adder. And of course you need to have these extra gates to complete or to get your adder subtractor circuit. So today I will explain a little bit how this circuit works. All right. So let's see. Okay, so now we have the full adder, and if we look at this, we use XOR gate for one of the input of the adder. So our adder and subtractor, we have X input and Y input. So two input, X and Y, and of course X is 8-bit and Y is 8-bit. But we can see here, we have the XOR gate here to uh, actually to convert this to complement number. All right, Y input to complement number, and it depends on one of the signal. One of the signal here, we call it add sub signal. So how this work? So we need to look at XOR operation. So for example, if you look at the truth table of the XOR, let's say this is M and N, this is output F. So we have 2 input, means that you have 4 combination. Alright, so this is XOR. Alright, the behavior or characteristic of the XOR gate. Yeah. So when we look here, we see, when we observe, we see that here when m equal to 0, all right, this part, when m equal to 0, f will follow exactly n. All right, f will follow n. All right, see, if n equal to 0, f equal to 0. Yeah. Well, n equal to 0, f equal to 0. When n equal to 1, f equal to 1. And when m equal to 1, we can see that f is the complement number of n. Okay. See, if 0, we have 1. If 1, we have 0. All right. So this is very useful when we use in our adder to design an adder subtractor circuit. So let's say we have an adder all right. One of the input is X. And of course you have C in, and of course you have C out here. And the output here is sum. All right. But here, when we use the XOR gate, and this is Y, all right. So, and we connect this signal together like this. And let's, for example, if this signal C in, or this signal we name it at sub signal. If this signal is 0, all right, so what is the signal here? If this signal is 0, so what is the input here? Okay, so if one of the input is 0, right, so the signal here is exactly will follow y, right? So this should be y. So if this is y and this is adder, a full adder, so the output here s should be equal to x plus y. So we can see that if the signal here is equal to 0, so this circuit will behave as an adder. But if this signal is 1, so we can see that if this signal is 1, the output here is a complement of this input. So this should be a complement of y, which is y bar. Alright? And if we see that if this is y bar and this is 1, C in is 1, so y bar is the first complement of y, and if and this is adder, means that this y bar, the first complement of y, will add to 1. Then you will have the second complement of this y. Alright? So you will have second complement of y as the second input, meaning that if this signal equal to 1, so we will have s equal to x minus y. Means that if the signal is equal to 1, this circuit will behave as a subtractor. Alright, so that is why we use the XOR gate, yeah, here. And this signal we name as at sub signal. And of course, when we want to have addition operation, so here must be 0. Yeah, that's why we have add. The signal label is at bar, means that it is active when the signal is 0. All right, add operation. And when the signal is 1, the logic is 1, so means that the sub is activated, and this logic will perform the subtract. All right, so that is why we have this, yeah, adder and subtractor circuit. And of course you need to do this in quarters. All right, so you need to have your 1-bit adder, and you combine that 1-bit adder plus this additional XOR gate, and you will have the adder subtractor, and the connection is like this. And you need to write your test bench code and simulate your circuit, and put in your report, and you need to discuss your result in the report. Right? So any question regarding the assignment, or maybe you can ask later in the WhatsApp group. All right. So we go to the next. The arithmetic overflow. So what is arithmetic overflow? This is very important in digital circuit and the arithmetic circuit. For example, we do the add and the sub just now. Sometimes, for example, right, when you want to add a number, for example, let's go back to this. For example, our system is 4-bit, all right? So let's say we have number 7, positive 7. All right, so in binary, 4-bit is that 0, 1, 1, 1, correct? And we want to plus with positive 1. So the result should be 8. All right. And positive 1 in digital or in binary 4-bit is 0, 0, 0, 1. Right. So when you plus this, you have 0, 0, 0, 1. Okay. But remember, in computer, the 4-digit number, the magnitude is only 3-bit. Yeah. The MSB, the last one is, yeah, the MSB, the last one is the sign bit. So this is sign bit. So in this case, we can see that the result is 0, which is wrong. And our MSB is 1. This indicates also that the answer is a negative number. Negative, yeah, because this is one, which is wrong, because we have number 7, which is a positive number, plus with positive 1, which is also a positive number, and the answer should be 8. All right. And when we add, we have a negative number here because our sign bit is equal to 1. All right. So this is wrong already. Okay. So what is the problem? So the problem is that our result here is not fit in a 4-bit system. Not enough space to store number positive 8 in a 4-bit system. All right. So when we look at this, yeah, 1000, when we go back to this, look at this, 100 into second complement number is minus 8, yeah, minus 8. So this is minus 8, which is wrong. Our result should be plus 8. All right. So the problem now is that the plus 8 cannot be fit in a 4-bit system. All right. Or in other words, there is not enough space to store plus 8 in a 4-bit system. All right. So go back to this. So arithmetic overflow is whenever our result from arithmetic operation not fit in our system, in our system. For example, our system is 4-bit. The result is not fit in 4-bit. Or if our system is 8-bit, the result is not fit in 8-bit system. So in 4-bit system, we need to look at what is the range of the number that we can fit in 4-bit system. So the formula is this. All right. So the result must be in this range. -2 to the power of n minus 1, and n is the size of your system. So in our case, it's 4-bit. So here -2 to the power of n minus 1 to power of n minus 1 minus 1. All right. So in our case, n equal to 4, right? So the 4-bit system. So what is the minimum number that we can fit in our 4-bit system? So must be 2 power of 3, right? So it should be minus 8. And the maximum number will be 2. 8 minus 1 should be 7. Okay. So this is the number that you can fit in 4-bit system. Very small, right? So that's why in your computer, the number is not, your computer is not 4-bit, but bigger, a lot bigger than this. Okay. And when we look at our result here, 7 plus 1 is 8. 7 plus 1, the result is 8. And 8 is clearly not fit in this range. All right, more than 7 already. That's why we have something like this. And this we call overflow. All right. Or in computer, the symbol is V, yeah. All right. Hope you get the idea. So this is very important for the computer or for the digital system to know that the result of any arithmetic operation is not fit in the space for the result. All right. So in digital system, you need to have the space for the input and also the result. For example, your adder maybe from the register. We will learn what is register in chapter in the next chapter, sequential design. So for example, this is 4-bit for A input, for example, and you have B input, another 4-bit register, and also you need to have your result in another register, which is 8-bit also. 4-bit also. So if the result is not fit in this register, in the 4-bit register, so we say that overflow has occurred. So this is very important to tell our system that the result is not fit in the in the result. So the system need to know and need to handle that problem. So that is the limitation of the hardware. So for example, you have your computer. Your computer may be 32-bit, or nowadays you have 64-bit computer. So if you have 64-bit computer, for example, means that the maximum number for arithmetic operation for your computer is 64-bit. All right. So for example, you have this 64-bit A and another 64-bit B. Your ALU will add. This is your ALU. Alright, and for example, if you have your result here in another register, which is 64-bit also, so when you add the number together, alright, if the result is more than 64-bit, alright, then your computer need to know that the number is actually need more than 64-bit already. So maybe it need to use two register or two 64-bit register to store the result. Alright, that is why it is important for the system to know whether the result can be fit in the result space or not. If not, you need maybe extra space to store your result. Alright, that is called the arithmetic overflow. Okay, now the question is how we design a hardware or the system that can detect the arithmetic overflow. Alright, so we need to go to the fundamental, to the operation of the arithmetic operation. Alright, so this is the maybe I use this one. Okay, the arithmetic overflow. So let's, for example, we have this arithmetic operation. All right, where we have one of the input is 7, another one is 2. Okay, so we add this number together and the result should be plus 9, positive 9. So when we add this number, okay, see the result here. 1 plus 0 is 1, 1 plus 1 is 0, and we have carry here, which is 1. All right, and we add again this to this one and to this one. We have, yes, 0, and of course we have carry here, and this carry is called C3. Yeah, this is C2, this is C1, right? Not that one, sorry. The carry for this one is C1, 1 plus 0. So this is C2, this is C3, and now we add again this one, 1 plus 0 plus 0, so we have 1. And now the carry, the last carry should be equal to 0, right? Because 1 plus 0 plus 0, we have 1 and no carry. No carry means that carry is equal to 0. So that's why we have C4 equal to 0, C3 equal to 1. Alright, for this case. And of course, we know that this is overflow. Because why? Because number 9, alright, we just learned just now that the limit for 4-bit number is from -8 to 7 only, and 9 is more than 7 already, so this v should be equal to 1, or overflow has occurred for this case. And let's look at the second case, this one, where we have -7 plus 2, and the result should be -5, right? And this is -7 in second complement number. Remember, in your computer, we use second complement number. Alright, so this is -7, this is +2, positive 2, we add. So we will have 1, 1, 0, 1, and this is exactly minus 5. Yeah, minus 5. And we see that when we add this number together, okay, 1 plus 0, we have 1. 0 plus 1, we have 1. 0 plus 0, we have 0. And now C3 is 0. And 1 plus 0, we have 1 here. And again, C4 is equal to 0. So that's why we have 0, 0. C3 0, C4 is equal to 0. And of course, here, V equal to 0. There is no overflow because minus 5 is still in the range. Alright? In the range. So, second possibility, when this number is negative and this number is positive, we have V equal to 0. And look at the third possibility. Alright, where now this number is number 2, is negative number. Alright, and we do the add. So we have this 0 plus we have 1, and 1 plus 1 we have 0, and we have carry here, and this is C2. 1 plus 1 plus 1 we have 1, and we have C3 equal to 1. 1 plus 1 plus 0 we have 0, and of course now C4 equal to 1. That's why we have 1, 1. And here we, is it overflow? Plus 5, no overflow. V equal to 0. Okay. And the last case, both of the number are negative. So this is minus 7 and this is minus 2. We add. We have 1 plus 0, we have 1. 0 plus 1, we have 1. 0 plus 1, we have 1. And now we have 1, and C3 is 0. No carry. But the last one, 1 plus 1 plus 0, you have 0. And of course you have 1 as your C4. Right? That's why we have C4 equal to 1, C3 equal to 0. And we can see that the result now is minus 9, which is overflow. Alright, and of course this will be V equal to 1. Alright, so the conclusion that we can make here is that we can have something like this. We have 4 combination of C3 and C4 here. Alright, the first case, the second case, the third case, and the fourth case. So we can have a conclusion like this. We have C4 and C3. We have 0, 0, 0, 1, 1, 0, 1, 1, and we have V here. So when 0, 0, here, we can see that V equal to 0. When 0, 1, here, we can see that V equal to 1. When 1, 0, here, we can see that V equal to 1. And the last case, when 1, 1, we can see that V equal to 0. Alright. So we have now this relation, alright, of C3, C4, and V. And when we observe this relation, it is clearly that this is the XOR gate. All right, means that we can get overflow by using XOR gate, where we have C3, C4, and we have V here. Okay, so that's why here we say that overflow is C3 XOR C4 XOR C4. All right, and this can be used for a bigger design, and we can have something like this. Yeah, so for example, our system is 8-bit. So to get the XOR, to get the overflow, if our system is 8-bit, we should be equal to C7 XOR C8. Yeah, so you can get the XOR. All right. Okay, so that is how we get the arithmetic overflow. Any questions so far before we go further? Okay, so we will go to here, arithmetic comparator. So now we have learned the adder, we have learned the subtractor, we have learned how to know when our system produce a result that is bigger than what our system can support, all right, which is the overflow. And next, in the computer also, or in any digital system, we always want to compare numbers, yeah, all right. So here we need to have a circuit or a system that can be used to compare a number, so that we can know, for example, we have two input, all right, A and B. So sometimes we want to know whether A is larger than B or not, or A is less than B or not, or maybe A is equal to B. All right, that can be done using a comparator. All right, so in digital system or in real life, right, how do we compare the number? We as a human, of course, very easy to compare a number. If I give you A is equal to 7, B equal to 6, so you can easily tell me that 6 is less than 7, right? But in your brain, actually, there is something happened, right? It's just like in the computer, all right? So in the computer, to compare a number, the best way is to use a subtractor. We subtract a number, right? Okay, so it's like this. It's something like this. So if you have two numbers, for example, A and B, A, B, so you want to know whether A is equal to B or not, whether A is less than B or not, or maybe A is greater than B. So what you will do, you can do this actually. If A minus B, if the number is more than 0, your conclusion is that A must be larger than B. Alright? Or if A minus B is a positive number, so of course A is larger than B. But if A minus B, you have a negative number, the result is negative. Alright? So we know exactly that A is less than B. Or if A minus B, we have 0, means that A must be equal to to B. Okay, so that is the logic. So to do this, very easy, right? Because we have the system already. We have the subtractor. We can do the subtract. And how do we know that the number is positive? We look at the sign bit, which is the MSB of the result. Yeah. So if sign bit is 0, means that the number is positive. And if the number is positive, so we know exactly that A is larger than B. All right. But if the sign bit is negative, we know that A is less than B. And if the result is 0, so we also know that A is equal to B. All right. So here is the comparator. See, we use the subtractor. So this part is the subtractor. So why is it subtractor? Because you see, you have x and this is y. All right. And y is complement here, and you have c0 equal to 1. When you have c0 equal to 1, means that the input here, all right, is at to 1. All right. And the input here is actually complement, first complement of y. First complement of y, you add 1, you can get second complement of y. So means that x is actually minus y. All right. So if the output here is x minus y, so we can check, yeah, the result, whether it is negative or positive here. Okay, by look at the sign bit. So where is your sign bit? Your sign bit must be the MSB of the result. Yeah, so this is the MSB. Okay, so we have the sign here, negative. So if the result here is 0, means that x is greater than y. If the result here is 1, all right, S3 equal to 1, means that x is less than y. All right, and we also have this. This is to check whether the output is 0 or not. All right, by using the NOR gate. Okay, so if all of the bit S here, or the result here, S3, S2, S1, and S0, all are 0, so we have Z equal to 1. Okay, so if Z equal to 1, means that all of these are 0. And all of these are 0, means that X and Y is the same, is equal. Alright, so if Z equal to 1, means that X equal to Y. Alright, and we may have another one, which is to check whether we have overflow or not. So you use C3 and C4 to the XOR gate, and you have overflow. All right, as simple as that. So this is a comparator where you can use to compare the number. All right, later on. Okay. And see here, you need to derive the Verilog code for the comparator. So maybe your homework, you do this, right? In quarters. Write the Verilog code for this and try to simulate and see what if you have give the input x equal to this and y equal to this, and look at the result. Okay, so that is the comparator, and the next one is the multiplier. All right, and should be the last part of this chapter. The multiplier is another one very important circuit in digital system, especially in microprocessor, and also in DSP chip, digital signal processing chip, where you need to multiply a lot to process the digital data. So how we design the multiplier? So to design the multiplier, we need to look at the fundamental theory, or how the multiplier or multiplication works, in at least in human view. And of course, when we want to implement in hardware, we need to use a binary number, a digital number. So for example, we want to multiply two numbers, 14 multiply with 11, and 14 here we call m, or multiplicand, and 11 here we call multiplier, right? And in binary, the multiplication is done like this, where we need to, just like we did in decimal number, where we have two number here. So we multiply, so this 1110 multiplied by 1, so we have 1110, and we multiply this again with the second digit of the multiplier here. So we have, because multiply with 1, we have the same number here, and this one multiplied with 0, so we have 0. This one multiplied by 1, so we have this, and we add all of this, we get this, and this is the product, or the result of the multiplication between 14 and 11 here, 154. Okay, so we can see that the multiplication in binary is easy. Multiply by 1, we have the number back. Multiply by 0, we get 0. All right, and we just add. All right, so when we have this, we can actually implement in hardware, right? But it is not easy to implement in hardware yet, because here we see we need to add many, we need to have many adder here. So we modify a little bit the process to this, to this, where we add first before we multiply again. For example, by using the same number, all right, we multiply here with 1. So we have this, we call it partial product 0, and we multiply with the second digit, all right, second bit of the multiplier, we have this, and instead of you multiply again with 0 here, we add first. We add the number and get what we call the partial product 1, and we have here. And then we multiply this with 0, we have 0, and we add again, we get partial product 2, this, and we multiply the last bit of the multiplier here, and we add, and we have the final product here, and we can see that yes, we can get the same result. But the advantage of this one is that we can use the adder, this part, because we have the adder circuit, and here also we have the adder circuit, so we can have this part, and here we can have the adder circuit, so we have this part. And also, to implement in hardware, the multiplication here, when we observe, it is equivalent to the AND operation, AND operation, AND operation. See, when we multiply this number with 1, we get this. Same as when we AND all of these bit with 1, we get this. 0 and 1, we have 0. 1 and 1, we have 1 and 1 and 1. So we can use AND gate to do this operation. And we can use adder to do this operation. Means that we can have AND gate and we can have adder. And when we compare this method to this one is easier to implement in hardware as compared to this one. So this is how we implement, or we translate that idea to the hardware. All right. So let's name this as M, and this is Q. So this is M0, M1, M2, M3, and this is Q0, Q1, Q2, Q3. So we have this, and we see this is M0 and Q0. This one is M1 and Q0, and this one is M2 and Q0, and so on. And this is M0 and Q1. All right, so I think, yeah, this is M0, Q1, and so on and so forth. All right, and we use adder to add this number together. And remember, M0, Q0 is directly go to P0, exactly like this. All right, this is M0, Q0. We sign to the final product already here, same as this one. All right, so we can implement this in hardware just like this. All right, so we see this. We want to implement M0, Q0, M0 and Q0. This is exactly M0, Q0, M0, Q0. We have P0 here. And this is M1, Q0, M1, Q0. Go to the one of the input of the adder because we want to add here. This is add, right? To get P1, PP1, partial product 1. All right. And add to what? Add to M0, Q1. So here you see M0, Q1. We add and we will have the P1 here. Exactly, P1. And again, for this one is M2, Q0, which is this one, M2, Q0. Add with M1, Q0. M0, M1, Q1. M1, Q1 here. All right, so we get M1, Q1, we get PP1 bit number 2. So this is PP1 bit number 2, where you need to use this to add to M0, Q2. Exactly here. Then you get P2. All right. So this is the structure of 4-bit multiplier, 4 by 4 multiplier, and you can see that when your input is 4-bit, right? Another input is 4-bit. Your result must be 8-bit, yeah. So the multiplier, the result is bigger than the input, yeah. So the result is the size of your input, the first input of the first operand plus the size of the second operand. In this case, 4 plus 4, you have 8. Yeah, 8-bit. All right. So if your system is 8-bit, 8 bits, the first operand is 8-bit, 8-bit. Another operand is 8-bit, so the result must be 16-bit. Right. So this is multiplier. And to design a multiplier, when we look at here, yes, we can use our adder. All right, how many adder here? When you have 4 by 4, 4 bit multiplied by 4 bit, you have how many adder? You have 12 adder here. See? All right. So that's why we say that multiplier is very expensive, because you see, one adder you have how many gates already? One adder. For 4-bit adder, if you translate to transistor, actually, you can have, if you use CMOS circuit, one full adder, you have 28 transistor. So 28 multiplied by 12. So how many transistor already you have? And this is relatively very small adder, because 4-bit only, right? So if you have 8-bit, so the size is quite big. So the adder, remember, the multiplier, the cost is very high. Yeah. So in your design, if you have many multiplier, of course your design will be big. So now, how to design this, looks like it is quite complicated, but again, because you can use hierarchical design, and this is modularity, right? You can reuse the design. You design the full adder and you use again and again and again, and you can do the connection like this. Or maybe because you see here, this one and this one and this one is, again, this is repeated, right? Maybe you can have something like this. Make this as a submodule. And again, if you make this submodule, your design will be looks simpler, all right, as compared to this, where here instead of this, you have one part here, you call it MUL1, this is MUL2, this is MULT, and you connect like this, and you get your multiplier, right? And again, you are required to derive the Verilog code for this as your exercise. So I will not give you a assignment for this. We will have another assignment later on in chapter 3 and chapter 4, a bigger assignment. But this one is as your exercise to understand the subject, the course better. So I will strongly advise you to practice, to do this. All right. This is very fun, actually, very interesting. Yeah. Okay, so that is the multiplier. And the last part will be the logic unit, arithmetic logic unit, or in short, we know this as an ALU. So the ALU is very important in computer design or microprocessor. So every single product that you have nowadays must contain at least microcontroller, all right? And every microcontroller or microprocessor must contain ALU. ALU is the core or the brain of your microprocessor, all right? So the basic operation of the ALU is actually like this, all right? So this is the symbol of your ALU, and you may have the A input, B, 2 input, 2 operand, and you have the operation, all right? So your ALU will be able to do many operations, depend on the size of your ALU, depend on your design, then depend on the application that you want to use. For example, if the ALU is for microprocessor, for your laptop, for your PC, for example, so the ALU may have uh, uh, many more operation as compared to this. And for this example, so we have only 8 operations, 8 operations. And of course, when we have 8 operations, the size for the control signal, here we call it control signal or operand. Operand, we have 8 possibilities. So for example, when the operand is 000, and the operation or the output of the ALU is A plus B. But if the operand is 001, so the output is A minus B. If 010, we compare A, B. If 011, A multiply B. 100, A and B. This is the logic operation. 101 is A or B. 110 not B. And 111 is pass A, means that we just pass A to the output here. And we have the signal here, Z and C, and please add one more signal, V. I forgot V signal. All right, this here we should have V. V. Okay. Let me. Okay, so you have You need to add another signal, V. Alright, can you see that? Okay, so that will be the ALU. So ALU is actually not very difficult to design. So because we just use what we have already, where for example we want to do this operation, so add, so we have the adder. We want to do the subtraction, so we will use the same circuit. Actually, adder and subtract is the same circuit. All right, we can do sub. Compare, we can use the same circuit also, because subtract, to compare, just now we learned that to compare a number we just use a subtractor, so we can compare already here. And for multiply, so of course you need to have a multiplier circuit, all right, in your ALU. And the AND operation is very easy, just AND A and B. The OR is easy, the NOT also very easy, and pass A is just pass the value of A to the output. So you can design your ALU after this. So again, case study, you are required to derive the Verilog code for this. So I will leave this as your exercise. So please take your time to learn and to do this. Very, very important. Who knows? I will ask you in the test. Okay. So that will be chapter 2. We are now done with chapter 2. We will have a short break, 10 minutes. All right. So you can ask question if you want to ask, if you have any question. All right. We will continue with chapter 3 in 10 minutes. So now is 10:22. So we will come back at 10:32.